Welcome to the 5-2 lesson on direct variation, also sometimes referred to as proportional relationships. Our objective, I can write and graph an equation of a direct variation. And so direct variation can describe a linear relationship. It's one of the four main types. So to lead off, you have to understand what a direct variation or proportional relationship is. And if a ratio of two variables is constant, so the ratio is consistently simplifying down to the same number, then the variables have a special relationship known as direct variation. As one varies, the other varies directly because of it. These relationships can be represented as a function in the form y equals kx, as long as k is not equal to 0, because that k, the coefficient of x, is your constant of proportionality, or your constant of variation. It's basically how much is it changing per some set interval. If it doesn't change at all, then, or in other words, if your k is 0, and therefore it does not change at all, it's not changing at all, and you're not going to have any change, so there's no variation at all. So as long as k is not equal to 0, there is some change over some interval, which means that something is changing over time in response to another variable. And so as long as k is not equal to 0, you have a direct variation equation. When a set of data points, for example, x, y, vary directly, k is that constant of variation, and it is the same for any two data points. The equation for k can be derived from that y equals kx, that equation for direct variation. So if you take the equation y equals kx, and then you were to divide both sides by x, you had y over x is equal to k. And so the k equals y over x is another famous equation that can be used to find the constant proportionality. We'll see that a little bit more in a second. But it's really just a reworking of y equals kx using literal equation skills. So how do you know if something is a direct variation relationship? And so the rule is, if it is possible to write the equation in the form y equals kx using literal equation rules, then it represents a direct variation. It's not that it's currently in the form y equals kx, it's that it is possible to get it in the form y equals kx. So let's look at some examples. 7y equals 2x. If I were to get that in the form y equals kx, I need to have y isolated by itself on one side of the equation sign, and you have a coefficient for x, and then no constant amounts. So let's solve for y. Divide both sides by 7. You get y equals 2 over 7x. There's no constant, and k is not equal to 0, so this is a direct variation relationship. For 3y plus 4x equals 8, you can kind of already see this is not going to fit that relationship, because when you solve for y, by subtracting 4x from both sides, you get 3y equals negative 4x plus 8. Divide both sides by 3. To get y isolated by itself, get y equals negative 4/3 x plus 8 over 3. And you can see right off the bat that 8 over 3, which is derived from the 8 at the beginning, is not going to allow it to fit that equation form y equals kx. If there is a constant, a number not associated with a variable, then it is not going to be direct variation. So this is not a direct variation equation. 9.2x equals negative 7.4y. I'm going to just switch the sides to make our lives a little bit easier, because then y is on the left, so we have negative 7.4y equals 9.2x. Divide both sides by negative 7.4. You get y equals negative 9.2 over 7.4. So that is your k value, and you have y equals kx. So it is possible to write that in this form, so it is a direct variation equation. And then the last one, 4x plus 5y equals 0. Your initial thought might be, oh, that 0 is a constant, not going to be direct variation. But if you rewrite it and solve for y, so subtract 4x from both sides, 0 minus 4x is just negative 4x. You get 5y equals negative 4x. Divide both sides by 5. Y equals negative 4/5 x. So the 0 is the only constant that doesn't influence whether or not something is a direct variation relationship. So all of these were direct variation, except for that 3y plus 4x equals 8, because the 8 makes it not a direct variation. So how do you write a direct variation equation? To write a direct variation equation, you need to find your constant of variation, your k value, using any ordered pair other than 0, 0, because we know that k is equal to y over x. But if I use 0, 0, 0 over 0 doesn't allow any change, so I can't use that one. We can then use it to find other values once we know our equation. So let's say y varies directly with x. Y is 35 when x is 5. What's the value of y when x is equal to 9? And so to do this, you're going to have to write a direct variation equation and then plug in x for 9. So let's start by finding your k value. K is equal to y over x. When y is 35, x is 5, so 35 over 5, which simplifies to 7. So k is equal to 7. So you can then write your direct variation equation. Y equals 7x. From here, we know x is equal to 9. So let's plug it in. Y equals 7 times 9, so y is equal to 63. So you have three different answers here. Your k value is 7, your equation is y equals 7x, and then we answered the question, what is the value of y when x is 9? The value of y is 63 when x is equal to 9. So these are three separate answers. You need your k to write your equation, you need your equation to find your y value. Let's do another one. Let's say y varies directly with x. Y is 10, x is negative 2. What's the value of x when y is equal to negative 2? So we do the same thing. K equals y over x, so 10 over negative 2, which is going to give us negative 5. So we have the equation y equals negative 5x. From here, we're just going to substitute in the value we know. We know that y is equal to negative 2, so we get negative 2 equals negative 5x. Divide both sides by negative 5. X is equal to 2 over 5, because a negative divided by a negative is a positive. So again, three separate answers. K is negative 5, y is negative 5x is your equation, and x is 2/5 when y is negative 2. The last thing we're going to cover is graphing a direct variation equation, and we'll do this through a real-world example. The weight on Mars, let's call it y, varies directly with the weight on Earth, let's call that x. The weights of science instruments aboard the Phoenix, Mars lander on Earth, and Mars are shown in this picture. So the weight of something on Earth is 130 pounds. The weight of that same thing on Mars would only be 50 pounds. What is the equation that relates weight in pounds on Earth and weight on Mars, and then graph this relationship? So just like on the previous slide, let's pause and take a second to find your k value. So k is y over x. The problem told us that Mars is y and Earth is x. So it's going to be 50 over 130. You can simplify that to 5 over 13. From here, let's write an equation. Y equals kx. K is 5 over 13. So y equals 5 over 13x is a fine equation. For the sake of what we're going to do on a graph, I'm going to round 5 over 13 to 0.38. It's not exactly 0.38, but it's close enough. Because now we need to graph it. So if you graph this, how are you going to do that? Well, table of values would be really helpful. Let's plug in some values. I don't know, 0, 50, 100, 150. Nice, easy numbers. And so if you plug in 0 for x, 0.38 times 0 is 0. Plug in 50. 0.38 times 50 is 19. Plug in 100. 0.38 times 100 is 38. Plug in 150. 0.38 times 150 is 57. You can then take these and plot them. So maybe a graph like this would be pretty reasonable. So you make dots or points at 0, 0, 50, 19, 138, and so on. And boom, you have your relationship. And so you can very clearly see some key characteristics which are important. So number one, the weight of something that weighs 0 pounds on Earth is also going to weigh 0 pounds on Mars. All direct variation equations go through the point 0, 0. Another thing you might notice is the slope of the line. So the slope of this line, doing some rough estimation, so I'm going to focus on the point 50, 19. To go from 0, 0 to 50, 19, you go up 19 and to the right 50. So your slope is 19 over 50. And that might seem familiar because if you back up and go back to your original equation, y equals 5 over 13x, your slope of the line is actually 5 over 13. And the slope of this line is also 5 over 13. For every 13 you move over, you go 5 up. And so rough estimate, 5 over 13 roughly translates to 19 over 50, which is actually really close because 19 divided by 50 gives you 0.38. And 13 divided by 50 is also roughly 0.38. So if you were to zoom in on your graph, you could go 0, 0, and then 5, 19, and then up 5 to the right 19, so you'd have a point at 19, 5. Just for the sake of argument, I picked easy numbers like 50 and 100 and 150, but it would all work the same. The slope of any direct variation equation is equal to k, because k is y over x, and that is true for every point, and slope is rise over run, delta y over delta x, and so k must be your slope.